Okay, so let's get started. Before I start the lecture, I'd like to make a few announcements. First announcement is about lectures next week. Unfortunately, I'm going to be out of town next week, and so I'll miss lecture. I much prefer doing a live lecture. Nobody likes to do a lecture to an empty room. But we're going to pre-tape the lectures this Friday, probably from 11 to 3. So if you guys are around, it would be really nice to have you here. So we'll pre-tape those lectures, and then they'll be broadcast during normal class time. So you can come during either slot. The other announcement I wanted to make is that, as you all know now, homework is due next week. There'll be no handouts in this class. Everything is online. So if you haven't already done so, download the homework from the website and get started on it. It's a little bit of a long homework, but it's a good review. And as I understand, your GSI has been doing some review on this material as well during the discussion sections. Speaking of discussion sections, Al has put up a makeup discussion section for Monday, and that's up on the board. Okay, any questions? Yes?
If it's more convenient, we can have a midterm next week.
Good idea. So there, anyone else want a midterm next week? All right, Al? Good question. So how do you turn in your homework? There'll be someone. That's a good question. We'll figure it out. I'll make an announcement on Thursday. We'll have a box or something. Actually, probably you can turn them into Rosita Alvarez, who's the assistant for this, administrative assistant for this class. And we'll tell you where to go to turn that in. Okay. Any other questions?
The class.
I'm not sure if it'll be available on webcast on the weekend. Don't know. Yeah. Okay. All right. Anything else? Okay. So let's get started on the actual lecture. This lecture today is going to continue our discussion of high-speed amplifiers, and more specifically, hopefully by the end of the lecture, we'll cover tuned amplifiers. And to discuss tuned amplifiers, we're going to have to review some simple second-order circuits, RLC circuits. So we'll spend a lot of time today refreshing your memory about second-order circuits. Okay, so let's skip ahead to where we left off. Just to summarize our discussion last week, we found that something like a common source or common emitter amplifier had a big bandwidth problem. It was very difficult to get bandwidth of omega t out of this amplifier, virtually impossible if we have any gain. So then we also looked at a common base amplifier, or common gate amplifier if you like, and we did some simple calculations and found that in fact it is very broadband. We found that under certain approximations the bandwidth is in fact has two poles both around omega t of the device itself. So common base amplifier is a very wideband amplifier stage. These are the poles that are due to this omega t is the pole due to the input. Omega L is the pole due to the output. So, excuse me, I misspoke earlier by saying you have two poles at omega t. Omega L, of course, depends on the value of RL and the value of C out, whether it's loaded by another amplifier or if it's buffered. This is the same calculation, assuming that the input impedance is matched to the source impedance. And this is something we're going to talk about a lot in this class, but before we talk about it, let me just kind of probe you guys and see how you feel about this issue. So why do we like to match impedances? And before you answer that question, let's review voltage amplifiers and current amplifiers. So as you guys all know, a voltage amplifier has a really high input impedance, so let's say high Z. And that means that the voltage gain is more or less independent of the source impedance you drive it with, because of this high input impedance, almost all the source voltage Vs appears across the input and gets amplified, right? And likewise, a good voltage amplifier has a low output impedance so that it can drive the full output voltage across the load, no matter what the load value is, right? Now, the opposite is true, of course, for a current amplifier. So for a current amplifier, we like to see a low input impedance because regardless, basically we want this to be ideally a short. We want the entire source current to actually go into the amplifier and appear at the output. Now all of a sudden in this class, instead of having high input impedances or low input impedances, we're going to do something funny and design matched input impedances. In other words, if this is RS, we'd like the input impedance Zin to equal to RS. Why do we do that? Okay, we use the mic.
It's so that we minimize the reflected power, and so we can have maximum power transfer to the load.
Very good. So we'll talk more about this a lot. Already, most of you are probably familiar with this. There's a maximum power transfer theorem that tells us that if we want to transfer the maximum power that we can from this source, and we can basically vary our load impedance, RL, the question is, what's the best optimal value to choose in order to transfer the maximum power? Now, if we're talking about transferring the maximum voltage, then we'd make RL infinity. That's a voltage amplifier. If we want to transfer the maximum current, we make RL equal to 0, and we maximize the current in the circuit. But to transfer the maximum power, we actually make RL equal to RS. Okay, and that's a simple two-line calculation. You can find the power in RL and take its derivative set with respect to RL, set it equal to 0, solve, and you'll find that that's actually true. Okay, any questions about that? Okay, so let's return back to the slide. So in particular, one of the nice things about a common base amplifier is that it has a low input impedance, roughly 1 over GM. So if we can basically tune the current in the device to get an input impedance match for a particular source impedance. And so using the same equation that we derived for the voltage gain, if we set RS equal to 1 over GM to get an input impedance match, we see that the gain degenerates into this simple form here. And the time constants, the time constants of the output are 2 omega t and omega L. So more than likely the time constant is going to be set by the omega L of the load. Okay, so these are just two examples of amplifiers. We saw one had the characteristic of having basically very bad bandwidth but good power gain. We saw the common base amplifier that has a reasonable power gain, but it has capability of providing input matching. And both of those amplifiers, of course, don't use feedback. So let's now look at an amplifier that uses feedback. And one of the simplest feedback amplifiers is a shunt feedback amplifier. It's simple because it's a single stage amplifier. Because we have the feedback is shunt with the input, shunt with the output, we call it simply just a shunt feedback amplifier. And what this amplifier does is it senses the output voltage and feeds back a current to the input. So our input really should be a current, not a voltage. Of course, we could take a voltage input like this and do a equivalent transform to a Norton form, and it's an input current. So if we do that, and you guys are going to do this in the first problem set, we find that the voltage gain of this amplifier is approximately minus RF over RS. And that's actually quite easy to derive. If we think of this amplifier, let's say this is the negative terminal, this is the positive terminal, as kind of a black box, then a shunt feedback amplifier looks something like this. So this is Vs over Rs. This is our equivalent current input. Rs is the input. Rf is the feedback. And you can see that if the input impedance were truly infinite, looking into the negative terminal of this device, then the gain, voltage gain, is simply minus Rf over Rs, assuming infinite loop gain in this system. And it doesn't take much work to also show that the input impedance is basically 1 over Gm multiplied by 1 plus Rf over Rl. So the shunt feedback amplifier has some nice properties. It has a gain which is set by ratios of resistors. So it's going to have good process, under the limit of very large loop gain. Its gain is going to vary very nicely with process and temperature because it's set by the ratio of two resistors. It also allows us to basically program the input impedance and get a low input impedance. Remember, without the shunt feedback, the input impedance is very high. So this allows us to actually, again, choose RF, RL, and GM to get an input match. Okay. Coming back to the slide, we can see that to obtain an input impedance match, we set GM-RS equal to 1 plus RF over RL. Usually, because the gain is really set by RF, and I say that because in most cases RS is fixed. It's something that you have to work with. So, in other words, your boss comes in and says, design an amplifier, has to have an input impedance match. The source impedance is 75 ohms. So you can't really change RS. And your boss will probably tell you what gain you need, so you can't really change RF. RF is going to determine the gain. And so looking at this equation, if RL is also fixed, then the only thing that you can change is GM. So in other words, you'll program your current large enough so that you get an input impedance match. And this is one of the reasons why this amplifier is much more popular with bipolar technology, because a bipolar device gives you much larger GM for a given current. So if you're trying to satisfy this equation with a FET, you might find out that you have to burn a lot of current compared to a bipolar. Okay, any questions up to here? Yes.
In the derivation of gain and Rn, you assume that the input impedance is infinite as for a voltage amplifier.
It's a large loop gain, actually. Yeah.
BJT is the
well, remember last lecture we talked about, we usually care about frequencies where the input impedance is dominated by capacitance, right? Of course, when you do the homework assignment, you're going to do the full-blown analysis. So here, a lot of times, what I really encourage you guys to do, even in the homework, is take several passes at the problem. When you first approach a problem, don't try to, solve all the gory details. Take a stab at it. Simplify the transistor. Say, let me assume this is infinite. Let me assume this is 0. Make some reasonable assumptions. Do the analysis, and then you'll get a really simple answer, right? Then you take a second pass at it and say, okay, now I'm going to include some of the parasitics. I'm going to include some of the things I neglected, and then you'll come up with a more complicated solution, which should simplify again back to that same derivation you did earlier. So what we're doing here is really taking a first pass at it, and in the homework you're going to take the second and third pass. Okay? So when you take the second and third pass in the homework, you're going to find that, for instance, if you do zero-value time constant analysis on this amplifier, there's two time constants, one due to the input capacitance and one due to the Miller capacitance. And again, if you make some approximations, you can show that this is roughly true, within a factor actually, that the voltage gain of this device times the 3 dB bandwidth is roughly the omega t of the device. Again, within some multiplicative factor. Okay? So again, if you're designing an amplifier and you're trying to optimize its performance, you would try to maximize, first of all, the device performance. You try to maximize the FT, and then you'd pick your impedances to get the gain and bandwidth that you can out of this amplifier. Okay? So I'm going very briefly through this because this is the topic of your homework. Don't want to bore you guys with it. One last thing I should mention is there are situations where this amplifier will interface where you need an amplifier that needs to interface from a low impedance up to a relatively high impedance, right? And because this is shunt feedback, both the input impedance and output impedance are relatively low. So if you need to interface it with another impedance level, whether it be higher or lower, you need to buffer it. So here I've shown an example of where you need to buffer this, let's say, to a voltage signal. coming here, we want an input impedance match because we want to maximize the power gain. But let's say the rest of the amplifier drives essentially voltages. We don't really need to be concerned with power anymore. So the input impedance of this stage may be the output impedance of this shunt feedback amplifier may be too low. So we can buffer this with, let's say, a source follower. And this also does some voltage shifting for us, which may be useful. One of the nice things about using an emitter follower, a source follower, is that it doesn't necessarily degrade your bandwidth. And that's because the input capacitance, even if this is a large device, the input capacitance is really bootstrapped. The source node or the emitter node more or less follows the base or gate node, and so the actual voltage across that capacitor is quite small. If you use, and it has positive signs, so if you use the Miller effect, you'll find that the effective capacitance is actually quite small. Another way to look at it is that the input capacitance is degenerated by the loop gain of the second stage. And so this is a nice way to not degrade the bandwidth of this amplifier. Okay. Questions or comments about that? Good. Okay, so now we're going to transition a little bit. I'd like to tell you guys about tuned amplifiers, but I just want to remind you guys about series and parallel RLC circuits. Now, before I do that, let me just introduce this topic a little bit. You know, up to now, we've been talking about designing amplifiers using R's and C's, right? So we have an amplifier like this. And, you know, we found that basically lots of RC time constants come into play and limit the bandwidth. And, you know, you may ask, well, why not use inductors, right? So for instance, if I take this same amplifier, which has some effective input capacitance, some effective output capacitance, let's say we do a Miller transform here, and if we know that this input capacitance is interacting with the source resistance to produce a pole, and the output capacitance is also interacting with the output impedance to produce a pole, why not simply put an inductor here to tune out this capacitance? Likewise, we could do the same thing at the output. We could just put an inductor here to tune out this capacitance. Now the input network looks like a parallel RLC circuit, and so does the output network. And so what are the properties of these kinds of amplifiers? And what are the limitations? How much bandwidth enhancement can we get? How high can we go in frequency if we use these techniques? So this is what we're going to hopefully get to by the end of the lecture. Before we do that, though, let's just quickly review some series and parallel RLC circuits. Okay. Now, I hope you guys aren't offended. This is kind of EX40 material, so it's really simple stuff. But at the same time, it's amazing how quickly we all forget, right? So it's good to go back and, even if it's simple, to review it. All right, we start out with this very nice, simple circuit. I have an inductor, a capacitor, and a resistor in series, and I drive it with a voltage source. And I can ask, what's the impedance looking into this circuit, right? Piece of cake. These elements are in series, so I have j omega L plus the reactance of this capacitor, 1 over j omega C, plus R. That's it. And I can factor this into real and imaginary parts. The real part is just R. These two terms are strictly imaginary. And if I factor out a j omega L, I have 1 minus 1 over omega squared LC. Okay? Now, what's interesting is that there is a frequency when omega squared is exactly equal to 1 over LC where this imaginary part disappears. And when that happens, that frequency we call the resonant frequency. And we'll see why in a moment. In other words, if we think about the impedance of this circuit, we know the impedance is basically the real part squared plus the imaginary part squared, square root. Since the real part is constant, then this impedance takes on its minimum value when the imaginary part takes on its minimum value. And that happens, of course, when it's equal to 0. So at this resonance frequency, we can also say that this series RLC circuit has a minimum impedance. Okay? Now, what's happening at resonance? You know, it's really easy at resonance to just say, well, at resonance, what's happening is that this reactance is equal to this reactance, but because they have the exact opposite phase, they just cancel each other out. So they're not even in the circuit. So I could, at resonance, redraw this circuit where I just short the L and C and I just see an R, right? But that's a little bit deceiving. Even though these are perfectly balancing each other out at resonance, it's a very, very careful balance. In other words, if I draw some vectors which represent the various voltages, now this is an IQ plane, let's pick a frequency below resonance. Now below resonance means that, remember, at resonance, this reactance is equal to this reactance, right? So below resonance, this reactance is actually larger than this reactance. In other words, because the same current is flowing into in the entire circuit, the voltage across the capacitor is larger than the voltage across the inductor. Okay, it's a question.
Oh wait, what is this diagram again?
Okay, so this diagram, what I'm plotting on the IQ plane, or I'm plotting on the imaginary, the complex plane, the voltages across the various elements, right? So this VR is the voltage across the resistor. There's some current. So let me actually write here what we're drawing. Good question. It's not very clear. So this is my series RLC circuit, and at any given frequency, some current flows through here, right? And that current is just Vs over Z. And I can define a VR, a VL, and a VC. Okay? Now VR is simply I times R. VC is 1 over j omega C times I, and VL is j omega Li. Okay? So we see that this is always real. This has is basically minus j 1 over omega Ci, and this is plus j omega Li. These two terms are imaginary. So if I plot these on a complex plane, the voltage across the resistor is always positive with this reference that I've defined, and it's always on the real axis. So this is VR. The voltage across the inductor has a phase of plus 90 degrees. Right? It's j omega Li. And the voltage across the capacitor is minus j 1 over omega Ci. Okay. Is that clear? Okay, so back to the slide. We can see that at low frequencies, the voltage across the capacitor is actually much larger than the voltage across the inductor, right? At very low frequencies, in fact, this is practically zero, and this is very large. So the net voltage is basically the sum of these three vectors. So if I take this vector and subtract it from this vector, and then add this real part, I have this net vector, right? If I go to high frequencies, it's just the opposite case. The voltage across the inductor is larger than the voltage across the capacitor. And again, I can do the same summation. What's interesting, though, is at resonance. At resonance, the voltage across the inductor in magnitude is exactly equal to the voltage across the capacitor. And their phase, of course, is always 180 degrees apart. So we can see now that these just balance each other out at resonance. Okay? Very simple, but actually has a very important consequence. So you might ask, well, what's the big deal? The big deal is that if we look at the voltage across, let's say, the inductor at resonance, it's simply, again, j omega naught L times I. And I, in general, is just Vs over Z, the impedance of the circuit. And we know at resonance, this obtains a minimum value which is equal to R. So we have the simple expression that at resonance, the voltage across the inductor is Q times the source voltage. Okay? And Q is basically omega naught L over R, as we've written here. Now what's interesting about the circuit is that omega naught L over R are things that we really have control over. So let's say I want to obtain resonance at, let's arbitrarily say 1 Hertz. If I make L larger than R, let's say 1 radian per second. If I make L larger than R, then the Q of this circuit is positive. That means that the voltage across that inductor is going to be larger than the voltage across the resistor. Now, how large can Q be? Well, it turns out it's a very important question, and we'll come back to this, but it's not unreasonable to design circuits with Qs of 10, 100, 1,000, even higher. In fact, you can design mechanical circuits which have Qs of million. So in this circuit, when current is flowing at resonance, the voltage Vs appears across R, right? But the voltage across this inductor and this capacitor can be actually quite a bit larger if the Q of the circuit is large. So imagine you put 1 volt here and you see 1 volt across the resistor, but you have a Q of 1,000 in your circuit. That means there's 1,000 volts across this inductor and 1,000 volts across this capacitor. Well, that's pretty exciting. We should be able to do something good with that. Okay? Questions or comments? Okay, and just as the voltage across the inductor gets multiplied by Q, so does the voltage across the capacitor. Well, that's obvious because their reactances are equal, right? And the current is the same. Of course, there's a phase shift. Okay? Now, in this circuit, it's very important to realize that we've defined a quality factor for the overall network. In other words, we've assumed that the inductor and the capacitor are ideal. They're perfect elements. Unfortunately, if you ever go out there and buy an inductor and capacitor, you'll find that they're not ideal, that they have some kind of basically series resistance, which is characterized by the quality factor of the component. So in other words, if I go out there and try to build one of these things, so I think I'm building this, again, a series RLC circuit, but I find that my inductor actually has some parasitics. So it has some resistance here, and my capacitor also has some parasitics. So the way the manufacturer will usually specify the parasitics is to tell you what the quality factor of the component is at a particular frequency. And that would be Q sub L. So Q sub L would be omega naught L over Rx, where we call this Rx, of that component. Likewise, QC is 1 over omega naught C R, let's say, Y. And this is the R that we insert into the circuit. So now we can see that the quality factor of the network is omega naught L divided by R plus Rx plus Ry. In other words, the quality factor is going to be lower than we thought when we were using ideal components. So either we have to make R smaller to compensate, or if we can't make R smaller, we just have to live with the lower quality factor. Question?
Yeah, so omega naught depends on L and C, right? So if you just have an inductor, how can you specify QL without knowing what the capacitor is?
That's a good question. So the manufacturer will tell you, at a given frequency, this is the Q of the inductor. And what they mean is if you took an ideal capacitor and hooked it up across that inductor, this is the quality factor that you would observe. Okay? That's a very good question. We're going to come back to that. So I just wanted to give you guys a preview, and I don't want to confuse you guys too much. Okay, so back to the definition of quality factor. So remember, up to this point, we're talking about the quality factor of the network, not the quality factor of the individual components. It's a little bit confusing. Well, you can see there are many equivalent ways of writing the quality factor. Omega naught L over R is the way we defined it, but at resonance, omega naught L is equal to 1 over omega naught C. So this is also an equivalent expression for the quality factor. But I also know that omega naught is simply 1 over square root of LC, so I can substitute that in here, and I come up with an expression which is that the quality factor is square root of L over C divided by R. And we usually call this square root of L over C the Z naught, or the characteristic impedance of the circuit. So the quality factor, which is a unitless parameter, is a ratio of two resistances. One resistance, which is square root of L over C, and the other resistance is the physical R of the circuit. Okay? Questions or comments? Okay. Let's do a little bit of math, and hopefully soon we'll switch to pictures, because pictures actually speak much louder than words here when we're talking about resonance. We can also, in addition to looking at the current in the circuit, we can also think of this as a transfer function, right? We can define the output voltage to be the voltage across the resistor and find the output voltage as a function of the input voltage, the source voltage. Now, because same current flows through the entire circuit as it flows through R, we can see that I drops out, and this is just Z of the series RLC circuit. And we can multiply numerator and denominator by j omega C, and we have this expression here. Now, does this expression make sense? You always can plug in a certain number of cases which you know to be true intuitively. For instance, a series RLC circuit can't conduct current at DC. So clearly the transfer function at DC should be 0. And that's certainly true because there's a 0 in the numerator. You guys also know that you can put second order circuits into standard forms, basically, or canonical forms. For this particular circuit, we put it into this form here. Basically, we just divide numerator and denominator by L and C, and we get this form. And we can now identify 1 over LC as omega naught squared. So let's just rewrite that. We can also identify L over R as, or R over L as omega naught over Q. So we substitute that here and here. And now we have a transfer function which is parameterized by two parameters, Q and omega naught. So omega naught is the frequency that we choose for resonance, right? And the quality factor is something that we would like to program. Let's see how important the role of the quality factor is. So what you could do is you could take this denominator and factor it, right? We could find the poles of the circuit. So if we just factor that denominator and assume that the quality factor is bigger than 1/2, we end up getting two poles, right? This is simple quadratic formula from 4th grade. So these poles basically have a real part and an imaginary part, and we can see that the real part gets smaller and smaller as the quality factor gets larger and larger. We can also see that there are two poles, they're complex conjugates of each other, and the poles for very high Q circuits are roughly determined by just omega naught. Okay? In fact, if we take the magnitude of these poles, that's the real part squared plus the imaginary part squared, and do a little bit of algebra, we see that the magnitude of the poles is constant. In other words, they lie on a circle. So here we can plot the poles of the circuit as a function of Q. And we can see that if the quality factor is bigger than 1/2, the poles lie on this semicircle. As the Q approaches infinity, if we go back here, we can see that the real part approaches 0, and the imaginary part just approaches omega naught. So we can see here on this root locus that this imaginary part is just omega naught, plus omega naught and minus omega naught. On the other hand, if the Q of the circuit is low, below 1/2, what we find is that the poles actually go onto the real axis, and the circuit becomes underdamped, as you know from simple second order systems. So if we want basically a very underdamped response, what we should do is make Q bigger than 1/2. If we want an overdamped response, or minimum damping, we would operate with Q less than 1/2. Of course, damping is just an equivalent way of talking about a circuit in the time domain. Damping and Q are actually related. Damping is basically inverse of Q, the factor of 2. Okay. Now, from a frequency domain perspective, the quality factor really determines the circuit bandwidth. So what I've done here is plotted this transfer function for different values of Q. Start out with Q of 1, Q of 10, and Q of 100. And what you can see is that the voltage transfer from the source to the load is exactly 1 at resonance. That makes sense because there's no voltage dropped across the L and C. They cancel each other out. But away from resonance, the circuit responds less and less. That's because either the inductor is providing a lot of reactance or the capacitance is providing a lot of reactance. The inductance will dominate above resonance, the capacitance will dominate below resonance. And just from looking at this plot, you might conclude that this bandwidth here, or let's say the 3 dB frequency, is really strongly a function of quality factor. Okay? In other words, you might say the selectivity of the circuit is very dependent on the quality factor. You might in fact be tempted to say that this circuit has infinite selectivity if it has infinite Q. In other words, if the circuit had infinite Q, this would degenerate to an impulse function, and the circuit would only respond at one frequency. It would reject all other frequencies. Okay? Questions or comments? Okay, and how do you find the selectivity? Again, this is a review. The way you would find the selectivity is you would find where the power drops by half. In other words, you take the magnitude of the transfer function squared, set it equal to 1/2, and find those frequencies where it's equal to 1/2. So a few lines of algebra, which are shown on these slides, in fact proves that the bandwidth of the circuit is exactly inversely proportional to the quality factor of the circuit. Okay? Comments, questions? All right? If I'm going too fast, let me know. If I'm going too slow, let me know. I know this is a review for a lot of you, but maybe for some of you it's not, so we need to regulate. Okay, good. Looks like it's not a review for many. It is a review for most of you. Okay, and it turns out that actually you can write the center frequency, or the resonance frequency of this circuit, as just a geometric mean of the frequencies where it drops by 3 dB. So that's also a cute result that you can derive pretty easily. Okay. Now series RLC circuits are fine. In fact, it turns out most of the time we deal with parallel RLC circuits. But there are many situations where a series RLC circuit is also important. Now, if you were a mathematician, you would just show this slide and say we're done, because a parallel RLC circuit is the dual of a series RLC circuit, and we don't need to rederive everything. It's true. It is the dual. Currents turn into voltages, the inductor turns into cap, so on and so forth. But it's probably good to go through and derive the results quickly, because the intuition between a parallel RLC circuit is very different. Keeping the concept of duality, instead of looking at the impedance of the circuit, we should look at the admittance. And then all the equations are exactly the same. So here's the admittance of the circuit. The admittance of the circuit is basically the admittance of the capacitance, j omega c, the admittance of the inductance, 1 over j omega l, and the conductance, g. And if you go back in 3 or 4 slides, you'll say, oh yeah, this equation is exactly the same, except the role of the capacitor is now played by the inductor, and vice versa. And instead of saying resistance, we now say conductance. Again, you can see that at frequency omega naught equal to 1 over square root of LC, plus or minus, the admittance is purely real. It just has a conductive part, just like a series RLC circuit. You can also pretty easily show that in this circuit, you basically have current multiplication as opposed to voltage multiplication. So in other words, if we look at the current IS, at resonance, all of it flows into R. That's because this admittance exactly cancels out this admittance. But again, so in other words, we could draw an equivalent circuit where we didn't have L and C. But if we go and look more carefully, there's a question.
Could you go over the concept of admittance a little bit?
Okay. So admittance Y is 1 over Z. It's just basically it's just a mathematical, more convenient to discuss admittance than it is to discuss impedance. In fact, we'll come back and talk about impedance as well. Okay. Yeah, it's just the inverse. So just like Z is a transfer function that if Z tells you, if you know the current, Z tells you what the voltage is, right? Y is the opposite. So if you know the current, you can find the voltage. Okay? So in other words, I have a source current here, and I want to know what the voltage is on this parallel RLC circuit. Okay? Other questions? Okay, so what's important, what happens, what's neat in this circuit is just like in the series RLC circuit where we had voltage multiplication, here we're going to have current multiplication. In other words, if we look at resonance, we find that the current in these branches is actually not zero. Let me draw a picture here. So at resonance, I find that IS, all of it, flows across R because these admittances cancel each other out. But if I actually look at the current inside of these elements, I find that there is a circulating current, let's say IC, which is Q times as large as IS, where now the quality factor is defined as R over omega naught L. In other words, the inverse of the quality factor of a series RLC circuit. Never confuse the quality factor of a series RLC circuit with a parallel RLC circuit. Okay? Now you can derive that the magnitude that this is true with a very simple calculation. The current in the capacitor is simply j omega naught C times V naught, because every element has the same voltage across it, and V naught is just the current source I divided by Y, the total admittance of the circuit. And at resonance, the admittance of the circuit is just G, or the conductance. Remember, the imaginary part is 0. And so now I can define quality factor as omega naught C over G. And so I can show, I've shown, that the current in the capacitors is equal to JQ times IS. Okay? Questions or comments? And of course, because the current in the inductor is exactly equal to the current in the capacitor with opposite phase, there's also current multiplication going on in the inductor. Now you can see that we can derive several expressions for quality factor, which are all equivalent. I can start out where I started before, omega naught C over G. Well, G is just 1 over R, so I put R on the numerator here. And at resonance, 1 over omega C is equal to 1 over omega L. 1 over omega C is equal to omega naught L. So I have R over omega naught L. And again, I can substitute for omega naught L as being 1 over square root of LC. And I have this other expression, which is the ratio of two resistors, R over Z naught, where again Z naught is a fictitious resistor, which is the characteristic impedance of the circuit. Okay, questions or comments up to here? Okay, so we spent a lot of time talking about the magnitude response. Turns out that in many applications the phase response is also equally important. And it's very simple to find the phase response. It's just the imaginary part, arctangent of the imaginary part divided by the real part. This is the imaginary part in the circuit. This is the real part. And basically I can now plot this. So I'll come here and do several plots. And what you find is that the admittance at low frequencies has a phase of minus 90 degrees, and at really high frequencies it has an admittance of plus 90 degrees. And it changes smoothly from minus 90 to plus 90 at resonance. Okay? Now the rate of change depends on the quality factor. If you have a small quality factor, it's a pretty smooth change. On the other hand, if you have a large quality factor like 100, it's a very abrupt change. And you can quantify that by showing that the slope of the phase response with frequency is exactly proportional to Q at resonance. So the larger the Q, the larger this slope. Okay? And again, we can do the same thing we did for the series RLC circuit. We can define a transfer function. For instance, we can define the current through the resistor as the output current relative to the current source. We write the equation down. We find it has exactly the same form as the series RLC circuit. We put it into the canonical form that we did also for the resistor, and it looks exactly the same. So it has all the same properties. The selectivity is a function of Q, and so on and so forth. Okay? And finally, often it's fruitful to think of the impedance of a series RLC circuit. Now, whereas the impedance of a series RLC circuit obtains a minimum value at resonance, a parallel RLC circuit obtains a maximum resistance at resonance, right? So coming back to the circuit, if I look at the Z of this circuit, I find that at resonance, it's equal to R, and away from resonance, it's smaller than that. So if I were to plot it, the impedance would look something like that, where it's zero at zero, because this inductor shorts the source at low frequency, and it goes back down to zero at high frequency, because this capacitor shorts at high frequency, and at resonance, omega naught, it's exactly equal to R. Now the shape of this curve is exactly the same shape of the curve that we derived earlier. It's basically the shape of this curve here. Okay, so this is a little bit more specific. If we look at the Z naught, the Z at frequency omega naught, and plugging in, we see these terms cancel out, and it's exactly equal to R. Now you don't need equations to tell you that, because you know that the L and C cancel each other out at resonance, and so the input impedance is naturally just R. You didn't have to write that down. And again, the bandwidth we find is inversely proportional to Q, just like we saw before. All right, so that's a quick review of RLC circuits. If you find that that was too fast for you, I encourage you to read the notes more carefully, come to office hours, talk to Al, review this material. And so now we're going to actually use some of these results and build amplifiers. Okay, before we move on to amplifiers, make sure there are no other questions. Okay, so let's go back to amplifiers. So what we have here is we have this common source amplifier, and for the moment I'm just going to voltage drive it. We'll see later that this doesn't really matter because I can always tune things out. We know the voltage gain of this amplifier is basically minus GM times the impedance seen at the drain of the device, right? And this impedance, of course, is just 1 over the admittance. Now we know that this impedance obtains its peak value at resonance, where this is just some R effective, where R effective is basically the effective parallel resistance seen in this circuit. Now, first of all, let's just make sure we see why this is a parallel RLC circuit. So let's redraw the circuit. So I have a voltage source here, and here I have basically C mu. I have CL, which is drain to bulk of this device plus any load capacitance. I have RL, and I'm adding an inductor L. And if I basically simplify this circuit, this is L, this is R effective, this is C effective, and this is GMVS, where C effective is CL plus C mu, and R effective is RL in parallel with the R out of the device. Okay. Is that clear to everybody? So we can see, going back to the slide, that the maximum gain of this device occurs at resonance, where this term here is maximized at a value of R effective. Okay. So So what are some of the advantages of this tuned amplifier? What have we gained by using an inductor? Okay. Why bother, right? Turns out that actually inductors, if you put them on chip, they're quite large. They take up a lot of area. So they, you actually only want to use them if you really can get a benefit out of them. Otherwise, you try to avoid them. Resistors are much smaller, or transistor loads, active loads, are much smaller. They come for free. Inductors, though, actually take up quite a bit of area, so we don't want to use them unless they really are giving us a benefit. So what are some of the possible benefits that we're getting from this inductor? Well, just naively, it looks like we can operate this transistor at any frequency we want, right? No matter how much capacitance we have in this amplifier, we can always put an inductor there to tune out that capacitance and have a resistive load at the frequency that we desire. So it looks like we can take this amplifier, which maybe had a 3 dB frequency of 100 megahertz, and now operate it at gigahertz. Okay? We'll come back to that. So let's go back to the slides. Okay, so here I also introduced the fact that in real life there are no perfect inductors and no perfect capacitors. So what we really have to also include is the effective shunt resistance of the inductor and the shunt resistance of the capacitor. And we'll, in a couple slides, figure out how to calculate those values. Now, if you look at this expression, you say, I want to maximize the gain. In other words, as may be obvious to you, I want to maximize the quality factor of the load. Okay? Well, let's not go there for now. Let's just say we want to maximize the resistance of the load. If you look at this expression for R effective, in order to maximize it, we should make the individual terms as large as possible. Now, R out is the R out of our transistor. We can probably play with the L of the transistor. We can play a few tricks to make R out as large as possible. But it turns out actually that for a lot of circuits, the R out of the transistor is actually quite large. Let's say it's kiloohms range. On the other hand, the R's of the inductor and the capacitor are something we have to live with. It's the manufacturer that gives us these parameters effectively. So the only way to maximize the R effective is to basically maximize RL. In the limit, we actually don't even put a resistor there, right? We just leave RL open circuited, and the R effective just becomes the effective resistance of the tank. So we can see that the maximum voltage gain of this circuit is the GM of the circuit times this effective parallel resistance. Now, jumping ahead a little bit, it turns out that if you build an integrated circuit version of this amplifier, the quality factor of the inductor is probably going to be much lower than the quality factor of the capacitor. And as we'll see, that means that this first term, really dominates. So the gain is just Rx, the parallel resistance of that inductor, times the GM. And what I'll show you guys in a couple slides is that the Rx can be written as the quality factor of that inductor times omega naught L. In other words, if I want to maximize the gain of this circuit at a given frequency, I need to find the inductor that has the largest quality factor. Otherwise, I have to burn more current to get a larger GM. Okay? Now, how do I make these conclusions? I'm jumping ahead a little bit here. What I need is this simple result, the series to parallel transformation, or shunt series transformation. When you deal with these RF circuits, especially these tuned amplifiers, often what you need to do is to convert elements like this into elements like this. In other words, I have a series resistance and a series reactance, and I want to convert it to a parallel reactance and a shunt reactance, shunt resistance, or conductance if you like. Now, I can do this at any given frequency, single frequency, right? As long as the impedance of the left-hand circuit is equal to the impedance of the right-hand circuit. Very simple. In other words, if Rs plus Jxs is equal to the parallel combination of these two elements, if I can pick Rp and Xp appropriately so that this equality is satisfied, then anywhere I see this circuit, I can reduce it to this circuit. Okay. Now, why do I want to do this? Okay. Let's come back to this picture here. In this picture here, I go out and I buy this inductor, and the manufacturer tells me, sorry, it has a finite quality factor of, let's say, 30. That means that there's a resistance in series with this inductor. Let's call it Rx. And QL is omega L over Rx at some frequency that you're interested in. Now you can see that this series resistance kind of messes up my analysis, right? Now I don't really have a shunt simple RLC circuit. What would be really nice is if I could convert this into L prime Rx prime in parallel. Then I can actually plug it into this equivalent circuit and everything is fine and dandy, right? So this is the motivation behind this transformation. Okay, so on the slide here, all we have to do is set the real part of this expression equal on the left-hand side equal to the real part of the right-hand side, and likewise we have to set the imaginary part equal to the imaginary part. Okay? I trust all of you can do that, and when you do that, you get that Rs is equal to Rp xp squared divided by Rp squared plus xp squared, and xs, I won't repeat it, is given by this expression. Now what's interesting is if I take the ratio of xs over rs, for a series element, that's how we define its quality factor. It's the reactance over the resistance. If I plug into this expression, there's a common denominator, so they cancel out, and what I get is Rp squared xp divided by Rp xp squared. In other words, I end up getting just Rp over xp, which is the way I specify the quality factor for something with a shunt resistor, right? A shunt RLC circuit. And so we can see that no matter how I put it in series or put it in shunt, just as you would expect, the quality factor shouldn't change because this is a mathematical transformation. So I can define a universal Q for this component, xs over rs, if I'm dealing with series elements, or Rp over xp if I'm dealing with shunt elements. Okay? And this Q helps me simplify this expression considerably. Because if I just plug in, divide numerator and denominator here by Rp squared, you can see that this turns out to be 1 over Q squared. Let me just basically jump ahead to the result here. You can show that the parallel resistance is equal to the series resistance times 1 plus Q squared. And likewise, you'll find that the parallel reactance is equal to the series reactance times 1 plus Q to the minus 2 power. Okay? And this is also a nice result because usually I have high Q circuits. So if high Q circuits, 1 over Q squared is small, so I can see that the reactance actually doesn't change much. Whereas the resistance, this small series resistance, turns into a large parallel resistance, and vice versa. Okay? Any questions about this transformation? Okay, so let's do an example of this transformation. So let's say that the manufacturer gives you a model for their inductor that looks like this. And what you'd like to do is use it in a parallel RLC circuit. So what you really like to do is to have an equivalent circuit that looks like this. Okay, so this is going to be L prime and this is going to be R prime. And let's say the manufacturer tells you that Q is 100 at, let's say, some frequency omega naught that you're interested in. Okay, so because this is a large quality factor, I know the reactance will not change. L prime is equal to L 1 plus Q to the minus 2 power, which is approximately equal to L. Okay. On the other hand, R prime is 1 plus Q squared times Rx, which is approximately Q squared times Rx, In other words, it's 10,000 times larger than Rx. So if this were 1 ohm, this is 10 kiloohms. Okay, so this is very simple. All I'm doing is transforming a series XR circuit to a parallel XR circuit. Okay, questions or comments? Yes.
In the limit case, when the DC where the Q equals 0 for series LC, can you explain why the parallel equals series resistance? Why RP equals RS in the case?
Okay, so this transformation, a very important point. I'm glad you asked this question. It only works at one frequency. So at the frequency of interest, the reactances are equal. If I move away from that frequency, these do not equal each other. Okay, that's a very good point. And that means that when I have this equivalent circuit, and I go from here to here, this equivalent circuit is only valid near the frequency at which I did this transformation. All right, good question. Okay, so now we can see where I did that calculation on the previous page, where it comes from. Remember, I want to calculate R effective. R effective is the effective resistance of the load tank. And in the limit, let's say that I don't use a load resistor, and let's say my capacitor is very good compared to my inductor, the only thing that will limit the quality factor of the tank is the quality factor of the inductor. And so here I take the series resistance of that inductor, which is, let's say, a few ohms, and I transform it to a parallel resistance. And that's roughly Q squared times Rx. And Q of an inductor, actually the R of this inductor is simply omega L over QL by definition. That's how I define the quality factor of an inductor. And so you can see that one factor of Q cancels out, and the final result is that R effective is simply Q times omega naught L. In other words, the gain of this circuit really is a product of Q times L, right? Because omega naught is a frequency that we want to operate at. So if you're looking at different inductors and you're interested in maximizing the gain, you shouldn't just look at the quality factor squared, as this expression is a little bit misleading. It really is just proportional to the quality factor. And so what about L? Why am I not free to use just any value of L? Because remember, the L has to tune out the effective capacitance in the circuit. So L is actually not a free parameter. The inductance value is chosen so that the resonance frequency of the circuit is the frequency where you want to operate. Okay. Does that make sense to everybody? Questions? Okay, so the fact that we can tune out capacitance is really the major advantage of this circuit. It means that, in theory, I can take my transistor amplifier, build it, and any parasitic capacitances, right, I can just tune them out. It seems too good to be true, right? And we'll talk about that. We'll talk about the limitations of that, some in this lecture, but certainly in future lectures. There are other advantages of this circuit. Another advantage of the circuit is that there's no DC drop across the inductor, right? No matter how much current I put through that inductor, because it has a very small series resistance, there's practically no DC drop. In other words, let me compare two amplifiers here. It's amplifier 1 and amplifier 2. In this amplifier, this is VCC, I have a drop, IR drop across this resistor, which is eating into the headroom. In other words, the output voltage here, I have to make sure this output voltage doesn't get too low, because if it gets too low, I basically put this device into saturation, excuse the terminology, and so then this transistor is no longer forward active and it can't provide gain. So that more or less limits how large I can make this current, or vice versa, how large I can make this resistance. And of course, we also know that this resistance also produces a time constant with this capacitor, and that also limits the bandwidth. Over here, though, the DC voltage is approximately 0 volts, right? Because there's a very small resistance in series with this, the winding resistance. And so the DC operating point at the collector here is actually VCC. And no matter how much current I put through here, this DC operating point does not move. So this thing always operates with the full available power supply voltage. Okay, question?
So we are only canceling the capacitor at one frequency. How about at the other frequencies? How does this affect the frequency response?
Very good question. That's exactly true. This is actually a tuned, what we call narrowband amplifier, meaning that we can only do this simple technique at one frequency. Now, if you're willing to play some games, you can in fact synthesize any transfer function you want. It's just like filter design. So I can pick multiple poles and zeros, right? And I can synthesize any transfer function I want, in theory, with any bandwidth that I want. In practice, though, you find that that's actually pretty difficult, especially because these inductors are large. So you don't want to have too many inductors in your circuit.
So this method doesn't cancel a pole.
No, what it does is it moves a pole, right? It's taking a low-pass pole and turning it into a band-pass pole. In other words, if I draw a picture here, transfer function of this circuit looks like that. Transfer function of this circuit looks like this. So it's taking this RC pole and moving it to an arbitrary frequency, apparently arbitrary frequency, omega naught here. And what we'll find actually is the bandwidth of the circuit does not change. So we'll come back to that point. Okay, so coming back to the other advantages of this circuit, we can see that headroom is a big advantage. Basically, I don't have to worry about reducing the headroom by using an inductor. In fact, it's even better than that. And the reason it's better than that is more subtle. Let's come back here. Let's again look at this amplifier. Let's say this is VCC. Now let's say VCE sat, is approximately 0, just to keep things simple. If I want to maximize the swing at the output, where should I bias the collector voltage?
Could you define bandwidth, like when you talked about it with the triangle versus...
Okay, bandwidth is the 3 dB bandwidth of the circuit. It's where the power transfer drops by a factor of 1/2. And bandwidth is a really loose, we speak of it very loosely. There's many different ways of defining bandwidth. It's a little bit frustrating when you're not familiar with the terminology, but hang in a few lectures and it'll start to make sense. Okay? All right. So, okay, I heard the answer out there. Someone said bias this at VCC over 2. Right? That's because if this is at VCC over 2, if I look at the output swing, I can swing all the way to VCC here. I can swing all the way down to 0 volts. Right? So when this is at 0 volts, that means there's lots of current going through this amplifier, pulling this voltage down. And when it goes to VCC, that means there's very little current going through here, and this voltage is pulled all the way up to the supply. Okay. Now let's look at this version of the circuit. So now, if I look at the collector voltage, its quiescent value is VCC. So as I, let's say, increase the current through this device and pull current through here, this goes below ground. This goes below VCC. On the other hand, you might be able to see that this voltage could actually go above VCC. That's because the voltage across an inductor is proportional to the rate of change of current. So if I'm increasing the current in this inductor, the voltage is positive. If I'm decreasing the voltage across this inductor, the voltage can go negative. And you can see when the voltage is negative, the collector voltage is actually VCC plus VL, above supply. Another way to look at this is that the average voltage across an inductor has to be 0. So if I pull it down, it's going to pull up in the same fashion. So in fact, we're going to analyze this in a lot more detail when we talk about power amplifiers and drivers. But the voltage swing I can get out of this circuit is a full VCC. In other words, I can get twice as much voltage swing from this circuit than I can get from this circuit. And that means that I can make my buffers and drivers and power amplifiers a lot more efficient. Okay? So that's something to keep in mind for the future. Alright, so now we can also make some variations on this tuned amplifier. For instance, we can do a cascode tuned amplifier. Again, cascode amplifier is really nice because effectively a cascode stage just looks like a normal transconductance stage. Has the same input impedance, but it has higher output impedance. Here that's a help because the higher output impedance means that we load the tank less. In other words, if I remember when we calculate the quality factor of this tank, it's all the resistors that appear in parallel at the output. So RL appears at the output, right? And the R out of this device appears at the output. But because this is a cascode device, its R out is actually much larger, larger by this degeneration of this device. So that means I can get a higher Q at the output. But what's a lot more subtle, and something that we'll discuss when we talk about oscillators and stability in amplifiers, is that the real benefit of using a cascode is it eliminates the parasitic feedback from the output back to the input. It turns out that when you use an inductor here, it's very easy to build an oscillator if you don't use a cascode, if you're not careful. And again, this is something we'll discuss in more detail in a couple lectures. But the reason a cascode is nice is it really essentially eliminates that feedback path, right? Also, you might note that a cascode does reduce the headroom a little bit, right? Because now this transistor, this node can't swing all the way down to VD-SAT. It has to keep, essentially has to keep this transistor alive. But because we gained all this headroom by using an inductor, it's really not too bad of an issue. It's not too much. Okay. So going back to your question earlier about the bandwidth of the circuit, remember, the way we define bandwidth, we found that for a second-order RLC circuit, the bandwidth of the circuit is simply related to the quality factor of the circuit. So the bandwidth of the circuit is inversely proportional to Q. And because this is a parallel RLC circuit, the quality factor is simply omega naught R times C. And you can now see that omega naught cancels out, and the bandwidth of the circuit is still just 1 over RC. Okay? So what this tuned amplifier has done is it hasn't made the amplifier wider band. It's just moved its center frequency from DC up to some high frequency. Is that clear? Questions or comments about that? Yes.
Question regarding the previous swing issue earlier. Frequencies you said the swing maximum with half VCC, for high frequencies it's full VCC. What's the consequence on the device stress?
Okay. Let's save that question for when we discuss power amplifiers later on. More than welcome to come to my office hour if you want to talk about that more. Okay. Yes.
The problem with CS or CE amplifiers was that there was another Miller-affected capacitance in the input.
Good
so
question.
Do we need another inductance on that side to tune it out?
Very good question. Okay, so the question is, I'll repeat it. We just kind of ignored the input capacitance, but remember, for common source amplifier, that input capacitance was actually quite problematic. So the suggestion is, can we do the same thing at the input to tune out that capacitance? And indeed you can. So in other words, this is Cn prime, which is Cn basically 1 minus AV, the Miller capacitance, which is basically, excuse me, C mu plus, let's say, C pi. And we've taken care of the output capacitance with this inductor. We can do the same thing on the input. Let's call this L1 and this L2.